This is video 3 for the sound unit notes. Again, we're going to do a little more review here. We've already talked about standing waves, so let's just quickly go back over through these. So standing waves are waves that appear to be standing still. It's a pattern that results when two or more waves with the same frequency, same wavelength, and same amplitude travel in opposite directions with each other and interfere. The ones you're responsible for will be standing waves on a string, standing waves in a tube open at both ends, and standing waves in a tube that's open at one end, closed at the other. So, some vocabulary again, just review. Our nodes is where we have destructive interference. Antinodes is where we have constructive interference. So, these are the first, second, and third harmonic. Standing waves on a string. When you hear a violin being played, you may think that there's only one standing wave on the string. However, there's going to be several standing waves on that same string at the same time, each with its own wavelength and frequency. And this means that the sound you hear from most instruments consists of multiple frequencies. The only instrument that you'll hear that only has one frequency would be a tuning fork, and a perfect tuning fork at that. Okay, so our harmonics. Remember that the model for this is n times velocity divided by 2L, where n equals all positive integers. So in other words, a harmonic is just some multiple of the fundamental. So if I asked you for the 17th harmonic, you would take 17 times the fundamental. And also notice that for a string, you have to have a node on each end. In a column of air, such as a wind instrument, we can have standing waves as well. Now, for a standing wave open at both ends, notice that we have to have antinodes at each end. So for this, it really doesn't change a whole lot. It's just that the math is identical as it is with a string. And there's a lot of similarities between the pipe open at both ends and the string. The only real difference is that a string has to have nodes on either end, where a pipe has to have antinodes at each end. Now, for a pipe that's closed at one end, open at the other, we must have a node at the closed end and an antinode at the open end. And this does change the math a little bit. This time it's over 4L, and n has to equal odd integers. So this time you have to be a little careful. If I were to ask you for the third harmonic, it would be 5 times the fundamental. So you have to be really, really careful when answering problems about pipes that are opened at one end, closed at the other. Now, with these, we can start talking about sound quality. And harmonics account for something called timbre. I know it's kind of spelled like timber, but it's pronounced timbre. Timbre is the quality of a steady musical sound, and it's the result of a mixture of harmonics present at different intensities. So if I were to take a look at a graph for a tuning fork only has one harmonic, the fundamental. So we would see a nice clean sine or cosine graph. There's a trick called a fast Fourier transform. And what it does is it takes a graph such as the sine graph, and it finds what frequencies are present in it. So for a tuning fork, there's only one frequency, the fundamental. If we take a look at something like a flute, there are multiple standing waves present. And what we do is we take all these different sine waves and we add them together. And we get something that looks like this. It looks a little jagged. It's the sum of all these different frequencies. If I did a fast Fourier transform on a flute, it would look something like this. And notice that this time, the second harmonic and the fourth harmonic are the most prominent, not the fundamental, not the first harmonic. That gives a flute its characteristic sound. A clarinet, the fifth harmonic, is the most prevalent. So basically what we do is, when we combine all of these harmonics, we get some interesting looking graphs. And you might have seen these in movies and whatnot, where someone's recording sound and you see these cool looking sine graphs. It's just a combination of all the different sine graphs from each individual standing wave. I'm not going to try to teach you how to perform a fast Fourier transform. That's some pretty advanced math. But there are computers out there that will do that math for you. All right, the final bit of review, talking about the effects of a moving source. This is the Doppler effect. Notice that when a source of sound is moving, it compresses the wavefronts in front. So we get, when we take a look at the speed of a wave, when the frequency, or when the wavelength becomes shorter, the frequency must increase. And behind the moving source, when the wavelength increases, the frequency must decrease. The speed of sound for in a medium, it's going to be constant, so the velocity of sound is going to be the same all the time. The Doppler effect works for every kind of wave, including light. So imagine that this train here is a star, and the star is moving. It's going to shorten the wavelengths in front of it and stretch out the wavelengths behind it. Now, there's a fun little acronym called Roygiv. And what this does is it shows you the order of colors: red, orange, green, red, orange, yellow, green, blue, indigo, violet, where as you move towards the violet side, the frequency increases. And as you move towards the red part of the spectrum here, the frequency decreases. So as the star is moving, the frequency is increasing. That's why we call it a blue shift, because the color is becoming more blue, and behind it it's a red shift because the frequency is going down and the color is becoming more like red. And then by looking at light coming from different stars, we usually have a pretty good idea of what their original color would be. We can determine if the stars are coming towards us or going away from us. And through this, we found predominantly a blue shift, which shows that the stars are predominantly moving away from us. And no matter where we look, we continue to see this blue shift. So that tells us that the universe is expanding. It's getting bigger. And finally, the way we calculate this, again, I'm not going to require any kind of math out of this, but the frequency that you received equals the frequency of the source, V plus or minus US, V plus or minus US. US is the speed of the source, so how quickly the source is moving. Actually, sorry, up here. Top one, UR. UR would be the speed of the receiver, so whether or not your ear is moving or not. Fs is the frequency of the source, Fr is the frequency of the received, V is the speed of the wave, so whether that's speed of sound, speed of light, speed of water waves, whatever that needs to be. Okay, this concludes the notes for the sound unit.